The motion of planets and celestial bodies has fascinated humans for centuries. From early astronomers to modern scientists, the question of why planets follow elliptical orbits has been a central topic of study and discovery. The answer lies in the laws of physics, particularly the laws of motion and gravity as formulated by Johannes Kepler and Sir Isaac Newton. The heliocentric model. The heliocentric model, proposed by Nicholas Copernicus in the 16th century, revolutionized our understanding by placing the Sun at the center of the solar system. This model simplified the description of planetary motion but initially still relied on circular orbits. Kepler's laws of planetary motion. Johannes Kepler, using the precise observational data of Tycho Brahe, discovered that the orbits of planets are not perfect circles but ellipses. He formulated three fundamental laws of planetary motion. Kepler's first law, the law of ellipses. Planets move in elliptical orbits with the Sun at one of the two foci. Kepler's second law, the law of equal areas. A line segment joining a planet and the Sun sweeps out equal areas during equal intervals of time. This means that planets move faster when they are closer to the Sun and slower when they are farther away. Kepler's third law, the harmonic law. The square of the orbital period of a planet is directly proportional to the cube of the semi-major axis of its orbit. This law provides a relationship between the time a planet takes to orbit the Sun and its average distance from the Sun. Newton's law of universal gravitation. Kepler's laws described how planets move, but it was Isaac Newton who explained why they move that way. Newton's law of universal gravitation states that every particle of matter in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. The elliptical nature of orbits. The influence of gravity and inertia. The combination of inertia, the tendency of an object to continue in its state of motion, and gravity, the attractive force between objects with mass, results in the elliptical orbits of planets. Here's a step-by-step explanation. Inertia. If a planet were only influenced by inertia, it would move in a straight line at a constant speed. However, this is not the case in our solar system due to the gravitational influence of the Sun. Gravity. The Sun exerts a gravitational force on the planets, pulling them towards it. This force decreases with the square of the distance, meaning that it is stronger when the planet is closer to the Sun and weaker when it is farther away. Orbital path. The balance between the planet's inertia, which tries to move it in a straight line, and the Sun's gravitational pull, which tries to draw it inward, results in an elliptical orbit. When a planet is closer to the Sun, it moves faster because the gravitational pull is stronger, and when it is farther away, it moves slower due to the weaker gravitational pull. Tidal forces. The elliptical nature of orbits affects various phenomena, such as tidal forces. The gravitational interaction between Earth and the Moon, for instance, leads to tidal bulges in Earth's oceans. When the Moon is closer to Earth, at perigee, these tidal forces are stronger, and when it is farther away, at apogee, they are weaker. Beyond the solar system. Exoplanetary orbits. The study of exoplanets has shown that elliptical orbits are common beyond our solar system. Some exoplanets have highly eccentric orbits, leading to significant variations in their distance from their parent stars, which can have profound effects on their climates and potential habitability. Orbital resonances. In some planetary systems, gravitational interactions can lead to orbital resonances, where two or more bodies exert regular, periodic gravitational influences on each other. These resonances can stabilize or destabilize orbits, leading to intricate dynamical behavior and sometimes elliptical paths. The elliptical orbits of planets are a fundamental aspect of our understanding of celestial mechanics, rooted in the gravitational interplay described by Kepler's and Newton's laws. This knowledge not only explains the motion of planets in our solar system but also provides insights into the dynamics of distant exoplanetary systems and the broader universe.